This is lecture 21 from Surveying 1, and in this lecture we're going to be discussing some applications of trigonometry. We've already used trigonometry a few times, but mostly in the case of what I call right triangle solutions. So I want to go a little bit beyond that. And trigonometry, as you might know, is a really important part of the calculations done in surveying. While there are many times in advanced surveying subjects where we use things like calculus and differential equations, most of the time we don't get into that, at least when it comes to doing the large majority of the surveying applications. But the basic algebra, the basic geometry, and the basic trigonometry is what I'm discussing about here. Now, this might seem pretty advanced for some of you who have not had much of a trigonometry background, but it's really important to get exposed to this now because you're going to see this come up again and again, if nothing else, because you need to know the theory to understand how those devices on which you push buttons to solve problems actually work things out. So we talk about right triangle solutions, and by that I mean when we have a right triangle, and a right triangle simply means that one of the angles in the triangle is 90 degrees, we are able to use the basic functions, the sine, the cosine, and the tangent to calculate the missing sides in these triangles. And one of the mnemonic devices that I've talked about earlier is SOHCAHTOA, where we say that the sine of an angle is equal to the ratio of the opposite side divided by the length of the hypotenuse. The cosine is the length of the adjacent side divided by the hypotenuse, and that the tangent is the ratio of the opposite side divided by the adjacent. So if we consider this angle, for instance, for this angle, the sine, and let me label some sides. Now, I know that many of you are used to calling the right angle C. I'm intentionally not doing that because it means that we memorize things a little too much. I'll talk about why that's a bad idea. So in this particular situation, the sine of angle C is what we want to calculate. The sine of angle C would be the opposite side, so that would be side AB divided by the hypotenuse, which would be side BC. And the cosine would be the adjacent side, side AC, divided by that same hypotenuse, which would be BC. And the tangent would be the opposite side, the AB, divided by the adjacent side, which would be AC. And this is always true. It applies to right triangles. Now you see here I mentioned a scalene triangle. What's a scalene triangle? A scalene triangle is basically where no angles are the same, no sides are the same, and no angle is a right angle. So in a situation like this, solving for missing sides is a little bit more complicated. And before we get into that, I just want to talk about the basic trig functions. So I've already talked a little bit about the sine, the cosine, and the tangent. You need to understand that these are ratios of the sides for angles up to 90 degrees. But then when you go beyond 90 degrees to 91, to 92, all the way to 360, meaning completing the full circle, there is a sine, a cosine, and a tangent associated with those angles as well. And it turns out the values are exactly the same, except that the algebraic signs change. And so you need to develop some understanding of how that goes. And so one of the things I want to do is, first of all, talk about developing an understanding of how these trigonometric functions vary as the angle changes. It's a really important thing to try to understand. So you should all know, at least at 0 and at 90, what these trigonometric function values are. So the sine of 0 is 0, the cosine of 0 is 1, and the tangent of 0 is 0. At 90 degrees, the sine of 90 is 1, the cosine of 90 is 0, and the tangent at 90 degrees is what we call undefined. I've written here the symbol for infinity, and that's because you have an opposite side that is infinitely long if you have a 90-degree angle. And then I just wanted you to look at these, because there are some interesting things that come out. For example, you should note that at 30 degrees the sine is 0.5. Now remember what the sine is. All right, the sine is the opposite divided by the hypotenuse. So what we're saying now is that the opposite side is half the length of the hypotenuse when the sine is 30 degrees. And conversely, if it's at 30 degrees, if you look at 60, you notice that the cosine is 0.5 at 60 degrees. And you see these other variations. I want you to kind of study this when you look at this PowerPoint to try to understand how these numbers change. Now if you look at the tangent, you'll notice that the tangent is 1.0 at 45 degrees. And why is that? Because it's the ratio of the opposite over the adjacent, and when it's 45 degrees, the opposite and the adjacent are exactly the same length. So a tangent of 1 is not a vertical line. A tangent of 1 is a 45-degree line, or what we sometimes call a 100% slope. And you notice here, when we get to the tangent of 60, we're at 1.73. At 75, we're at 3.73, and goes very fast to infinity. So one of the things I want to draw for you crudely, and I want you to go to a textbook, or you can find many good reference articles about this on the internet, and look at the plot of the sine, cosine, and tangent functions. So it turns out if the sine, let me use a different color, if the sine is 0 at 0 degrees, so what are we plotting here? So what I'm doing is plotting on the vertical the size of the function, whatever that value is, and on the horizontal I'm plotting the angle. In each case, the center here is 0, or more correctly 0, 0. So the sine is 0 at 0 degrees, and the sine is 1 at 90 degrees. So if we draw this, that's what we have, and I'll just show those 2 points for right now. Now, when we have the cosine, it's actually 1 at 0 degrees, and it's 0 at 90 degrees. And then the tangent is 0 at 0 degrees, and at 90 degrees, it's actually infinity. So it's way off the page here somewhere. But at 45 degrees, it's at 1. So it looks something like that. Now, if we looked up these angles or computed these angles for all the other values, we would find that the sine actually looks something like that. And then if you went from 90 to 180, it would do this. And then if you went from from 180 to 270, it would do this. And from 270 to 360, it would do this. So in 360 degrees, you see that the sine is positive here, negative in the second half, from 180 to 360. But it does the same thing. So it's a mirror image down here. I'm going to take this off because this is intruding into my cosine curve. But that's what I wanted to understand. But if I go backwards, we would get this. Now, I don't know if you know this, but we can have the concept of a negative angle. For example, an azimuth of -30 would be the equivalent of a bearing of north 30 west or a positive azimuth of 330 degrees. So we can have the concept of negative angles. So that's what the sine, and sometimes we call this the sine wave. Now, the cosine, on the other hand, looks like this. And then if we plotted it on down, it would actually look like this. So this is 0 to 90, 90 to 180, 180 to 270, and then 270 to 360. So the cosine is negative between 90 degrees and 270. It's positive again between 270 and 360. And again, I'm going to take this off. The cosine curve, as you can see, is kind of a mirror image, but it's offset. So what we've done is taken the reading or the value of the cosine curve and offset it back to the x-axis. That's the only difference. If we superimposed both of them, it would look something like this. I'll use a different color. So if we superimposed the cosine curve on the sine curve, it would look something like this. So I'm going to take that off, but they're exactly the same curve. It's just a matter of where they start, but they go up and down between zero in the middle with +1 and -1 as the extremes. And then if we look at the tangent actually goes up something like this. And then it's called an inflection point. It changes and goes up something like this, so that at 90 degrees, it's at infinity. And that's should be more of a straight line, more of a smooth curve, I should say, that goes up like this. And that's at 90 degrees. So again, these are all at 90 degrees over here. And if you look at these functions in a textbook, you will see it better explained for all the others. So one of the things that is a useful thing to do is to actually create a table like this for every quadrant. In other words, this goes from 0 to 90, but to do another one from 90 to 180, and 180 to 270, and then 270 to 360. So that brings us to the other functions that are used to solve scalene triangles. So we have a law called the law of sines, and it simply says that a divided by the sine of a is equal to the ratio b divided by the sine of b, which is equal in turn to c divided by the sine of c. So I can just simply label three angle points, a, B, and C. We always use capital letters for the angle points, and then we use lowercase letters opposite the angle points that are the same letter. So this would be side C, this would be side B, and this would be side A. So what this is saying is that if we take the length of side A and divided it by the sine of angle A, which is this angle here, and then we took the length of B and divided it by the sine of B, which is this here, we would get the same result. We don't know what that result is, but we know it would be the same. And then the same could be said with C over the sine of C. So this is a really important law that you need to remember exists. And some of the examples are when you're doing triangulation to find a horizontal or vertical position, or other lines that cannot be directly measured. So let's do an example problem. You must, to be able to use the law of sines, know an angle and a side opposite the angle plus another side or an angle. So for the example that I'll work, I'll have a known side. So we have here point C, point A, and point B. And we don't know what this looks like, so it could be the triangle doesn't even come out anything like this. I've just labeled it so that we can start to imagine. So angle C over here is 36 degrees, 15 minutes, 43 seconds. AC is 246.35 and AB is 185.67. We can already see that my triangle is not quite right because, no, actually that could be okay. It looks roughly like that shape. Since I haven't drawn anything to scale, we don't know. So what we can do then is set up our equation. So let me go back and just show you that again. It's A over sine A and so forth. By the way, if you forget and you do sine of A over A and sine of B over B and sine of C over C, that's okay, because it turns out that those are just reciprocal fractions and the relationship still holds. So in this case, I'm going to take 185.67, which is this distance over here, divided by the sine of 36.15.43, and that would be equal to 246.35, which is side AC, divided by the sine of B. Sine of B is what we're solving for. So now, relying on some of your algebra, you should know that you can do some substitutions and what's called cross multiplying. So we can write that the sine of B times 185.67 is equal to the sine of 36.15.43, and I looked it up, 0.59148. And if you remember in that earlier table, I showed that the sine of 30 was 0.5. So this is one of those reasons why it's nice to know when you punch up a trigonometric value for an angle, whether it's roughly in the ballpark. So it's equal to the sine of C times 246.35. And then to solve for this, you would actually divide both sides of this equation by 185.67. And if you did that, then this 185.67 cancels with the one above it. So we get on this side, the sine of B is equal to this number here. So you run through that relatively simple algebra. Don't forget when you do this that you've got degrees, minutes, and seconds. So you need to convert degrees, minutes, and seconds to decimal degrees. And you get out of this that B is 0.78478. But that's the sine of B. That's the sine of B. And so now you take the inverse sine of B, the reverse function, and we get that B is equal to 51 degrees, 42 minutes, and 2 seconds. So that's how you use this function, and you'll be doing some exercises to try this out. Now that's one way to do it. The other way to do it, or the other way you apply the law of sines, is a slightly different problem where you know an angle and a side opposite plus, in this case, another angle. So we have that angle C is 3615.43, angle B is 55.0000, and AB is 185.67. So it's in this situation, it's possible now to solve for all the other sides. By the way, let me just let you know that these were your givens. You were given angle C, you were given side AC, which is this one here, and you're given side AB, which is this one here. From doing this calculation, you now have been able to solve, there's a different color, been able to solve for angle B. So you still don't know angle A, and you don't know side BC. But hopefully you see that you can now calculate it from a number of different ways. One way that you can do this would be to first add angle B and C together, subtract it from 180, so you can solve for side angle A, and once you have angle A, you can use the law of sines again and solve for the unknown side BC over the sine of angle A, which you now know. So just realize that even though I just solved for one side, that once you get that one side, now you can get on a roll and solve all the other sides in the triangle. And that's pretty much the way these all work. Now the law of cosines, which is a little bit more complicated looking. So the law of cosines says that any side squared is equal to the sum of the other two sides squared minus 2 times the product of the other two sides times the cosine of angle C. So that sounds pretty complicated, but let me just point out something with our right triangle. You all know the Pythagorean theorem, and we often do it this way. And too many people remember it this way, that C squared is equal to A squared, I should be using lowercase letters. So C squared, the hypotenuse, is equal to A squared plus B squared. Now you see the similarity here. What we are saying is when you don't have a right triangle, that's really inconvenient. It doesn't help us to solve it. But it turns out some wise guy, probably a Greek, may even be Pythagoras, discovered that if we apply the correction to A squared plus B squared, which is what we use for a right triangle, if we applied this correction, we would still be able to take the square root of this whole shebang and get side C. And the way he said that is you take the length of A, the length of B, multiply those two together, then you multiply them by 2, and then you multiply by the cosine of C. And remember, C is no longer a right triangle. So applying it here, let's say this is A, this is B, and this is C. And you want to find out the length of this line here, side C, which is also called AB. So you'd use it the same way. You would take this side squared, which is known, this side squared, which is known, minus 2 times one side times the other side times the cosine of angle C, which is known. Now, that is a very complicated set of operations to do on your calculator, so it's really easy, if you are not familiar with this law, to make a lot of mistakes. But once you get around being organized and methodical in your head to get this done, it's a real handy thing to have. So here's the typical use. When you have an angle and two adjacent sides, that's the most common way it's used. So in this case, we have that angle C is known, And in my particular sketch, I call this A, this B, and this C. So C is known, it's 29, 15, 42. AC is known, that's 279, 42. And BC is known, that's 303, 58. So you see here it's the included angle between two known sides. Included angle simply means two known sides, they intersect to form an angle, so the angle between them is called the included angle. So this allows us to calculate the opposite side. So very simple. I'm going to use the equation as I presented it. So we would wind up with AB squared, right? AB is the equivalent of side C, so AB squared is equal to 279.42 squared plus 303.58 squared minus 2 times 279.42 times 303.50. Times the cosine of the 29, 15, 42. So if you substitute into this, really the only substitution you have to do is go find the cosine of 29, 15, 42. So you have to convert that to decimal first, then hit the cosine function, multiply that by 303.58, by 279.42, and by 2. That gives you this whole thing here. Then you square 279.42 and 303.58, add them together, and subtract these off. And when you subtract them off, you get AB squared, which it turns out will be 12,480.742. I like to carry my intermediate calculations out 1 or 2 decimal places, and then when I take the square root of that, I get side AB, which turns out to be 111.72. And you notice that I didn't use any units, because this could have been in feet, in chains, in meters. It doesn't really matter as long as you have the same units. But very simple application, but kind of tedious and takes a lot of organization. It involves being very careful about how you put your writing down on the page and keeping it all organized so you don't mess yourself up. The other way you can use the law of sines is when the 3 sides of a triangle are known. And when 3 sides of a triangle are known, you have to use the equation a little bit differently, because if you remember what the law of cosine is, it says c squared equals a squared plus b squared minus 2ab cosine of angle C. Well, in this case, what are we going to do? What are we doing? We're trying to solve for side C, for angle C. And so when you're solving for angle C, that means we can substitute 100 squared for c squared and so on and so forth. And then when we get to cosine C, that's the unknown. So we have to do this math where eventually we wind up having to solve for the cosine of C. And that is definitely a case of where if you haven't been paying attention to how you do algebraic manipulation, you'll wind up in a lot of trouble. So something you want to think about, because we will be doing some exercises using the application of the law of cosines to this type of problem as well. Now, when you use the two laws together, you can sometimes do useful checks on the measurements that we have done in surveying. It gives us some idea of the accuracy. So in this case, I just want to talk about, we have a point and we have a line that exists. So there's a point at each end of the line as well. Okay. So that's our situation on the ground. And we need to make some measurements, but we don't have some way of completely doing a complete traverse for some reason. There may be an obstacle, it may be a ravine, it may be a river, it may be a building. There can be all kinds of things that get in the way. So let me just show you, so we could make that distance, we could measure from our known point over to one end of this known line. We could measure this line from our known point to the other end of the line. And from that, we can actually calculate, and then if we can measure this angle in here, we can calculate using the law of cosines, or the law of cosines, you could calculate the length of this line and compare it with what our data tells us that line needs to be based on previous measurements. And this is something we often do, and some of you may recognize a situation involving some field work that many of you have probably done that you maybe have forgotten, but you measured 5 sides and you also measured 5 angles. You also measured 2 of these diagonals. And you may or may not be able to see easily that you can use the law of sines and cosines to check on the accuracy of your measurements in other ways than the straightforward way of simply adding up all the angles to see if they add up to n minus 2 times 180 and so forth. So we'll be working on some exercises that use that information as well. And with that, we will conclude this lecture.